Okay, so today we're talking about Riemann sums and the definition of a definite integral. So far in our class, we've looked at the integral of some function. And then when we take the integral, we end up back at our original function, so there should be no prime there. Back at our original function, f of x plus c. So this is the indefinite integral. And the reason it's called an indefinite integral is because it's not an exact value because you don't know what the c value is, okay? It's indefinite, meaning like you're not sure what c is, okay? Definite meaning positive. So you're not positive what c is here. A definite integral allows you to solve for that c value. So before we can start talking about the definition of a definite integral, we need to talk about Riemann sums. Okay, so let's look at the area under some curve. So I'm going to draw some curve. And I want to figure out the area from A to B. Now, when we're calculating the integral, I know we want to break it up into equal width rectangles or equal width trapezoids. In this situation, we're just thinking about a Riemann sum, so we don't need things to be equal width, okay? So I can go ahead and just draw rectangles kind of however I want here for this example. They should be touching though, so that was a mistake. There we go. Okay, now each of those rectangles has a different width, and I'm going to zoom on this picture just so I can make sure it's really clear for you guys. So each of those rectangles has a different width, and our width is determined by our x value. So I'm going to go ahead and, because our widths are a change in x, I'm going to refer to them as delta x. So this one right here would be delta x1. You don't need this, okay? This width right here would be delta x2, delta x3, delta x4, and then this big one would be delta x sub 5. Okay, now, so those are our widths. Now we need to figure out the heights of our rectangles. So the heights of our rectangles are determined by the height of our function, right? Where black curve intersects our rectangles. And as we talked about in class, you can take a right limit, a left limit, or from the center point to figure out your height. Here in this situation, I'm just going to kind of go with the center point. So if I call this point C1 on my x-axis, then I can call my height here f of C1 because I define my function as f of x. So this would be f of C1. If this was C2, I could call this height f of C2. My height for this triangle, this rectangle is there. So that's C3, so this one will be f of C3, and if I skip ahead, I'm all the way here, which would be f, the height would be f of C5. Okay, now, I can use these heights and these widths to determine the areas of my rectangle. So I can say that this rectangle has area of my height times my width. So f of C5 times delta x5, okay? This area here is f of C3 times delta x sub 3, okay? And then I can keep going. So if I look at my first one, this would be f of C1 times delta x1. Now, when I add up all the areas, and I would obviously have to add up this one and this one too, that's how I end up with my Riemann sum, okay? So we could say then that the Riemann sum of a function f on the interval AB, remember this is the interval notation we talked about in class, so on our interval AB is written as r sub n for Riemann sum is equal to, and then that's the sum symbol, the sum from k equals 1 to n. So we start at one rectangle and we go up to however many rectangles we had, right? Like in the example we did in class, n was 6, so we'd put a 6 here, of f of c sub k times delta x sub k, okay? And we would add all those together. So Riemann sums are important. Now, in the example I did, I told you the partitions, or the width of our partition, so we can call each of our rectangles like a partition. So delta x represents the width of the partition, okay? Doesn't matter. I told you the width doesn't matter for Riemann sums, which is true, but when we talk about the integral, we know the width does matter. So, sorry, move this up. So, hang on, let's take a step back. So that's our height of our rectangle. That's not how you spell height either. What's wrong with me here? How come it won't erase? Okay. My eraser's not working, so we're just going to cross that out. So that's the height of the rectangle, and this is the width. So for Riemann sum, our height and our width don't matter, but we know that the whole purpose of today is to talk about the definite integral, and you know that those things matter, or the width matters, all the widths need to be the same in an integral. Okay, so let's go ahead and write that down. So for an integral, all delta x's need to be equal. Okay, it doesn't matter what they're equal to, they just need to be equal. Now, in this example I did above, I didn't care where I measured the height from my triangles, or I'm sorry, in my rectangles, but you should care in a integral, right? So, because here I didn't care, but in an integral I do care, let's look about what would happen to our Riemann sum if all of our widths were the same, okay, and all of our heights were taken from the right, the left, or the midpoint. So, let's think about what would happen to our Riemann sum then, or the area under our curve, if when we took all of our triangle, or all of the area of all of our rectangles from A to some point B. So just for today, we're going to break it up into 4 rectangles for this example. So if I'm always going from the left in this example, my area for those rectangles, the sum of that area, is always less than the sum of my curve. See how my curve, I have these missing gaps, right? So I know my area would be below my curve. So in that case, I would call this L sub n, which is the lower Riemann sum. Okay, now, if they were all above the curve, so again, I'm going to break it up from A to B and partition it again into 4 things. If I were to take my rectangles from the right this time, sorry, that last one is not correct. My area would be below my curve, okay? Or I'm sorry, my area would be above my curve, so we would call this U sub n, which would be the upper Riemann sum. And if we were to take it from the midpoint, we would call that, so this is A, that's B. So if we were to take it from our midpoint, we would call that M sub n, which would be the middle Riemann sum, because it's in the middle. Okay, now we're going to use all this knowledge about our lower, upper, and middle Riemann sums, and this situation here, to understand how the definition of indefinite integral works, okay? So this is the crux of what we're doing today, and this will kind of be the end of it. So let me just move this up so we have more space. So the definition of a definite integral. So keep in mind, guys, that the definite integral, that's when we're allowed to solve for that c, that constant at the end. We don't know what it means. So if a function is integrable, meaning you can take the integral, integrable, you can take the integral on some interval, a comma b, then the integral, and since we have these end points of our interval now, we add those to our integral symbol. So we're going to put a little a here and a b there. So then the integral from a to b of some function f of x dx is equal to the limit as delta x approaches 0 of the lower limit, or lower Riemann sum, and that's also going to be equal to the limit as delta x approaches 0 of our upper sum. So what it means as delta x approaches 0 is that for our curve, the width of our rectangles are getting smaller and smaller. So right now they're pretty small, right? If I went from A to B, if I did it again and made them smaller, okay? You want them tiny. You want like your widths, the widths are tiny. Widths are very small, okay? They're so small they're approaching 0. Okay, so that's it for today. We're going to do examples in class next time I see you guys.